me open that file also. Yeah, you are asking about this realization of this, right?
Yes, sir.
So 1 over s plus 2, you understand how to realize this transfer function?
Sir, we can just have e to the power minus 2t times ut.
No, no, no. I'm not asking about its impulse response. Okay, so like with integrators, adders, and like multipliers, etc. So uh, look at this diagram. For example, we have an integrator here. So if this is y dot, then if you integrate y dot, you will get y. This multiplier, you can make this as minus 2. Okay, so here y dot is equal to x minus a times y. Okay, so yeah, uh, so this is this term, and so this diagram, do you understand that this can give you 1 over s plus 2 if you choose a appropriately?
Yes, sir.
Okay, and now we want to have s plus 1 also in our transfer function. So okay, so this realizes 1 over s plus 2, and now okay, so let me go here. So we have realized this 1 over s plus 2 with with some block. And now we want to realize s plus 1. So this is my y1, let me say. This is x. And, yeah. Now I want to do the following. I want to give in y1, sorry. Let me call this maybe h1. So here I want to give in y1, and yeah, I want to obtain y. Okay, so y of s is s plus 1 times y1 of s. This is fine, right?
Yes, sir.
So from here now, yeah, using without introducing any differentiators, because yeah, we want to avoid differentiators because they are not causal. We want to construct whatever I just showed. Yeah, this. So y1 of s, sorry, y of s is y1 of s plus s times y1 of s. So s times y1 of s is same as differentiating y1, but we don't have to differentiate y1 because that is already available to us from here. Okay, so what you do is you take have an integrator block here. This is y dot. Let me not draw the rest of it. So there is something here also, and this is y. Sorry, y1. what you do here is you have just a constant multiplier. So yeah, this is just y1 of s as it is, and this you take it from here. This is y then. Okay. So y of s is s times this is y1. Yeah. Y of s is s times y1 of s plus 1, which we wanted to realize. Is that clear?
Yes, it is clear now.
So now
So,
shown it for uh, yeah, transfer functions, rational functions of order 1 or less than order 1. So yeah, this is strictly proper, and for proper transfer function where numerator degree is equal to denominator, which is yeah, s plus 1 over s plus 2, we have seen how to realize. Okay. So degree 1 rational functions, you know now from this diagram how to realize that. So for higher degree rational functions, you have numerator degree say of say p and denominator degree say q. Then those transfer functions you can write it like this. So some transfer function, some factors will have just constant terms in the numerator, etc. And all of that you can put in cascade like this, cascades of this type, and that should realize yeah, whatever you want to realize. So this is, by the way, just one way, okay? There are other ways also which you can refer to in the book. Yeah, I'm just giving one way to realize a given transfer function, and this tells you, like in hardware, how should you interconnect your components to get that specific transfer function. So I hope this is clear.
yes, sir.
Any other questions? Okay. So yeah, there was one more thing I wanted to explain more thoroughly regarding this. So I hope this is fine, but yeah, I did not get a convincing yes last time. So yeah, let me be more precise here, okay, so that everyone gets convinced about this. Yeah, so let me spend 5 more minutes so that yeah, this is resolved once and for all. Okay, so recall this. If we take u of t, then clearly this is not integrable, right? Yeah, integral of this is infinity. Everyone knows this. So this is u of t going off to whatever infinity. Yeah, because the area under this rectangle is infinite since width is infinite. Now if you shift it to some finite real value, let's say u of t minus tau, like, the area still remains infinite, right? It does not matter if it starts from 0 or some other finite value. Yeah. And even if you scale it by some amount, so yeah, for example, yeah, if you take from t1 and some scaled version of ut, scaling by some non-zero constant, something like this, the area under this curve is still infinite. So I hope everyone buys this. Yeah. Anyone has any objection to this? Yeah. You cannot have any objection to this because yeah, no one can deny that area under these curves are infinite. Okay. So with that, then let us see what happens. Yeah, if this becomes constant. So uh, so let me call this product as f of t. Okay. So what we have is a limit t tends to infinity. F of t is equal to some constant c. Okay. So as t tends to infinity, f of t converges to c. C is some constant. So let's look at this from first principles. Okay, by going into definitions of limits. So what does it mean that as t tends to infinity, f of t tends to c? So given an epsilon, epsilon could be anything. For all epsilon, this should be true. No matter which epsilon you choose, there exists t naught such that, so this is such that given an epsilon, epsilon greater than 0, there exists t naught such that for all t, this is for all t strictly bigger than or equal to t naught. If I take this difference f of t minus f of t naught, taking too long to write this. This must be strictly less than epsilon. Okay. So given an epsilon, you should be always able to choose this t naught such that this difference is strictly less than epsilon. If this is true for any epsilon or for all epsilon, okay, then that is what this means. Okay. So let's do this pictorially. So if I am given any epsilon, I should always be able to choose some t naught such that for all t to the right of this, so this is c, f of t comes within epsilon distance of that. So let's call this epsilon. And okay, so for all t greater than t naught, f of t is somewhere in this band, okay, epsilon band. Yeah, forever it stays within this band. It cannot go out of this band. That's what it means when we say something like this. Okay. And yeah, that is basically the trick which is going to work for us. Now I can choose any c1 strictly less than c, strictly less than such that this happens. So this is my c1. So f of t is strictly bigger than c1, and yeah, it is converging to c. Okay, and now I can take this u of t minus t naught because t naught is finite from this, such that f of t is strictly bigger than, yeah, sorry, this is c1 times u of t minus t naught. So f of t is strictly bigger than this, and yeah, it is converging to c, and this area is infinite. So area under yeah, f of t is greater than or equal to area under yeah, this lower bound, and that is infinity. So hope that convinces everyone once and for all, yeah, why this, had this been constant, then Laplace transform of xt will not exist because yeah, the Laplace transform of xt will diverge by this argument. Okay, so this can be rigorously shown. Yeah, anyone still not convinced about this? Okay, so yeah, I hope this convinces everyone. So with that, then yeah, we can start with filters and sampling then. Okay, so what we are going to do now is the following. We have, I think, 8 classes left, if I'm not mistaken. So I will try to finish filters and sampling. Filters, yeah, should be straightforward now. We have everything we need to understand filters. And yes, some of you might have already read this or at least given it a thought. Yeah, I asked you to think about some questions a few weeks back and so forth. So this we should be able to finish at least max to max late by next Thursday. So filters, sampling, and yeah, some examples also. So you can already have a look at these examples. I will discuss them yeah, either Wednesday or Thursday, depending on yeah, when we finish the theory part, and that will be the end of sampling. So by Thursday we should be done with sampling and some exercises. So I think there are 4 or 5 exercises here. 2 examples on sampling. So they are also there in the problem set. I don't have time to discuss all, but yeah, at least 2 slightly challenging problems. Not too challenging, but anyway, I will discuss. And then, yeah, some stuff related to Laplace and Z transforms also, and some filter design related problems. So I think there are 4 problems which I want to discuss. 2 regarding sampling and 2 regarding that bilinear transform, connecting Laplace and Z transforms and some filter design. So these problems I will discuss yeah, Wednesday and Thursday. So by Thursday, I want to be done with this. And then we still have, I think, 4 classes left. So I will discuss some system properties, dynamical systems and stuff. So yeah, I think we will get some time after that. So yeah, if there is any topic you guys want me to discuss, then yeah, please let me know. May not be right now immediately. If you can suggest something which you would like to see, yeah, just type it up in the chat box. And yeah, I will see if I can uh, if it is completely new to me, then yeah, I may not be able to discuss it with yeah, too much insight or anything in the given short time. But feel free to yeah, suggest if there is anything specific you would have liked to see in here. So random systems or whatever, I don't think we are going to get time to discuss that. But yes, in last 1 or 2 lectures, yeah, we can decide depending on yeah, your suggestions. And if there are no such suggestions, then I will see depending on what I feel like. Yeah, we can discuss something. Okay. So either today or by next week, yeah, please let me know. All right, so let us start with filters. So we had already seen sink and so this is sink in time domain. So the side lobes decay to 0, but yeah, they go to 0 at infinity. Okay, so this continues. This is in the frequency. So this is our ideal low pass filter. Okay, with a cutoff frequency. Yeah, this is called cutoff frequency. So omega c and minus omega c. C for cutoff. Okay. All right. So let us understand this in detail now. I think everyone should get this. So is this causal, by the way?
No, it's not.
Yeah, because yeah, for t less than 0, we have a non-zero ht. So any ideas to make this causal? Can it be made causal?
So multiply by ut.
Okay. So there is one suggestion: multiply by ut. But that's going to cause some distortion, right? So we'll get something like this. This left lobe, yeah, is going to vanish. So in the frequency domain, we are going to get a distortion, right? Because this is we are not keeping our original impulse response intact. We are cutting the negative part completely. Okay, so clearly this is not going to give us ideal low pass filter, right? So let's think about stability. Is this stable?
Yes, sir.
Okay. So why is it stable? Someone said yes. So can you justify why it is stable? Okay, no one is saying anything now. This is not stable, by the way, because this is not absolutely integrable. So to integrate this, then this diverges. So ideal low pass filter is neither stable not causal. Yeah. So that is pretty bad. Instability, usually when you have a system, you don't want unstable system. Okay, you would like to have your system stable because yeah, instability implies something inside blows up. Okay, some values shoot off to infinity, can shoot off to infinity for some initial conditions or some inputs, etc. So at least while designing, we would like to avoid unstable systems. And if you have non-causal systems, then yeah, if the underlying parameter is time, then this is not realizable if the system is non-causal. Okay. So this is a big difficulty if we try to realize ideal low-pass filters. Okay, in hardware or whatever. Yeah. So in theory, this is fine. Conceptually, yeah, mathematically, yeah, you can have functions like this. But yeah, building a circuit or a system which has this impulse response or this frequency response is impossible because of causality. Yeah, and instability is just something which we would like to avoid. Okay. Unstable systems are not good in some sense. So yeah, these are the difficulties in realizing ideal low pass filter. So being non-causal, yeah, you cannot realize non-causal system. So ideal low pass filter is not realizable. It's just a theoretical concept which we use to understand signal processing, etc. So any ideas? Yeah. So we have lost both stability and causality. So and we would like both. So yeah, one suggestion was to multiply h of t with u of t. So that resolved causality, yes, but yes, there is going to be a big distortion in the frequency response. So I don't know what the frequency response of this looks like. Yeah, you are going to get a convolution of this with whatever the impulse, sorry, whatever the Fourier transform of u of t is. We had seen Fourier transform of u of t, and depending on that, yeah, we are going to get some shape. So any other ideas apart from this? Okay, I'm not getting any suggestions. So Yeah, someone wants to.
Sir, can we shift the a few lobes from the negative side to the positive side
Right.
and then multiply by ut?
Uh, yeah, yeah. So that's a good suggestion. Right. So I mean, the main part of the impulse response is inside this main lobe, right? And then these are the side lobes. Of course, if you cut off the side lobes, then yeah, that is going to introduce some distortion. But yes, you would like to keep this main lobe at least. And yeah, how to keep the main lobe and preserve causality is to shift this to the right and then chop off the side lobe. So if you do something like this, so this is at 0, whatever, and this is at T naught. So in principle, if you delay this by infinity, then okay, you can make it causal, but yeah, that's again not possible. You cannot have infinite delays, because if you have infinite delays, yeah, I mean, your system will never work. It will work at infinity, whatever. So, yeah, you put as much delay as you can, but yeah, you cannot have a arbitrarily long delay. And then you cut off, maybe at here, and here also. If you have a finite width, okay, so erase this, something like this, and if your function is nice and bounded within that uh, finite finite time interval, if the function is yeah, nice and bounded within a finite interval, it is always integrable, absolutely or whatever. So you preserve both stability as well as causality, but you lose something. Okay, of course, you are chopping off this side lobe, which are going to cause some distortion in here. But yeah, it is relatively minor distortion. Okay, because yeah, you are not chopping off the significant lobes. Slightly insignificant lobes is what you are chopping off. Okay, so that is the trick. Shift it by some finite amount and then restrict it to some finite interval, so that it is both causal and stable. So is that fine? Why it is causal and stable if we use this trick? It should be straightforward, right?
Yes, sir.
Sir, can you explain the stability part of this trick once?
So if you have a function which is defined over a finite interval, and that function is bounded, okay, so it I don't know, maybe oscillates or whatever, but does not shoot off to infinity anywhere, then the what I'm saying is the area under this curve is always going to be finite. Okay, because you can always as long as your function is bounded, yeah, so it can take negative values also, of course, but let's take absolute values. So we are integrating absolute values of our function, and our function is nice and bounded. So yeah, whatever it may do something, but it does not shoot off to infinity. Yeah. Because why I'm considering this is because our underlying function is nice and bounded. Yeah, the sinc function, it does not go to infinity anywhere. Yeah. There are no discontinuities also. It is nice and smooth. And now we can bound this as long as yeah, this is nice within some finite interval, just bounded by some constant. Yeah. And area under this is finite. Yeah. This upper bound, maybe capital M or whatever. So if we integrate, yeah, a bounded continuous function over some finite interval, it is always finite because you can always bound that by some constant function, and area under this constant function is finite.
Yes, sir. Got it.
That's why you have quote unquote nice function over a finite interval. The area under that function is always finite, and that is what we want for stability. Okay, so both causality. Yeah. Yes.
Sir, how we clip the remaining part?
Yeah. Remaining part you don't get. That's what. So ideal low pass filter. You cannot realize it even with delays. So this is some approximation is what we are doing of ideal low pass filter, and the frequency response of this chopped off approximation is I don't know, something which may look like some distortion, something like that. And okay, here also there could be some distortions. So it's not going to look like this ideal cutoff frequency, and so of course this is an approximation, and you are throwing away the insignificant side lobe to get stability.
Sir, how we achieve that?
Okay, how we achieve that? So you shift it. Okay, so this you shift by some T naught. So that's what we are doing here, and then you multiply that with some rect function. So let me write that. HT, let me not write it. Sinc of T minus T naught you do. Okay, and then this looks like and then you multiply that with rect some width. Okay, so maybe I choose rect centered at T naught up to 0. Okay, so this is my width maybe 2 T naught. It's up to you. However, so here I'm choosing a rect function of width twice T naught centered at T naught, and then I will multiply this sinc function by this rect function in time domain. So this is again in time domain T minus T naught, and that's going to give me this finite width approximation.
Sir, can we multiply it with step function?
Multiply with step function. If you multiply it with step function, then there is one problem. On the right hand side, you are going to keep all the side lobes.
Sir, we can multiply by u of 2t naught minus t, that it will reverse the step function, and then we can multiply.
Reverse the step function, then you are going to keep the left side lobes, right? And I mean that you anyway want to throw away because that is going to cause non-causality. So can you repeat what you said?
Sir, we can do like, if I tell you the entire function, it will be like sinc of t minus t naught into u of t into u of 2t naught minus t. So
Yeah, so u of t into u of 2t naught minus t. So sinc of t minus t naught, let me write what you said. Just correct me if I'm writing something wrong. This is the first one, and what do you want to multiply with? U of t?
u of t into u of 2t naught minus t.
Okay, u of t into u of 2t naught minus t. u of 2t naught minus t, it will look something like this. And u of t, yeah, you are multiplying. So yeah, you are going to get a rect function, right?
Yes, sir, exactly.
Yeah, so this is fine. This is what I was also saying. Instead of yeah, defining it using yeah, this multiplication, I just said rect. So yeah, this is fine. Yeah, so rect you can realize it in whichever way, yeah, you want to. So this is one way, u of t times u of 2t not minus t. There might be other ways also. I'm not sure, yeah, but this will surely work. Okay, so this is the idea: shift and chop off the side lobes after after you decide about some finite width. This would ensure both causality and stability. Okay, so ideal low pass filters, yeah, we cannot realize, but we can do these approximations, which I had just described. Okay, so let's look at what low pass filters we can realize. So yeah, our familiar exponential function and yeah, its frequency response. So this we already know, and if you plot the frequency response of this, if I am plotting a frequency response, let me not write it. So 1 over a plus j omega, its magnitude response is going to be square root of a squared plus omega squared. So this is 1 over squared plus omega squared. So at omega equal to 0, is going to be a 1 over a. And as omega goes to infinity, yeah, we are going to get 1 over infinity. Okay, so it's going to decay to 0. So something like approximately. As omega increases, the denominator value also increases, and yeah, 1 over whatever decreases. So this is a low pass filter because yeah, at high omegas it attenuates the gains, and at lower values of omega, okay, this has a higher gain, and this can be realized using an RC circuit. You have a resistor and a capacitor. Okay, and if you connect that okay, to some source, sinusoidal, whatever, and this is an example of a low pass filter. Not ideal, of course, but it is still a low pass filter. Okay, R and this is called first order filter. Why? Because the transfer function is 1 over s plus a. If you write down the differential equation form of yeah, V of, so this is our VO of T, voltage across the capacitor, and this is VI. If you write down time domain expressions of VI versus VO, then you get first order differential equation. So with either that, or you can look at the transfer function of yeah, this system VO of S over VI of S. The degree of the denominator polynomial is 1. That's why this is the first order low pass filter. can have filters like this also. So just check that. Okay, if you have L and C, this is also a low pass filter, but this is a second order low pass filter. Okay, because the order of the transfer function is going to be 2 in here. L and C. And you can have higher order low pass filters also. Okay, in general, higher than 2. So why do we want to use higher order low pass filters? Is because yeah, we know that we cannot realize this in practice, but we can get close to this. Yeah. So first order filter yeah, gives us something like this. Second order filter, okay, because you have more degrees of freedom, it can give slightly better responses. Maybe more flatter. I don't know. I have not checked this. You can actually plot and see. But as we put more and more degrees of freedom in our filter, yeah, we are going to get better and better approximations of the ideal low pass filter. This one. It comes at a cost also. So yeah, you are going to get ripples also as you put more and more terms, something like this. Okay. But yes, you have more sharp cutoffs like this compared to yeah, the cutoffs which are very coarse in this case, for example. So you finally settle onto some trade-off. Okay, so you can decide what order filter you want to realize. Okay, you are going to get so yeah, depending on the type of filters, there are Butterworth, Chebyshev, etc. So there are some filters where you get very flat responses, okay, over some finite interval, okay, and then you have cutoffs like whatever. So these are better approximations of the ideal low pass filter, something like this. And those you can realize by yeah, using more and more R and C or L, R, L and C, all of that, etc. So that comes with practice and yeah, whatever you will. If you want to learn these design skills, then yeah, you can take filter theory or DSP courses, and there you can actually learn the design techniques. But I hope you get the idea at least. Yeah, what we are trying to do and the philosophy behind yeah, realizing the better and better approximations of ideal low pass filter. Okay, so more degrees of freedom you have, yeah, of course, more tuning parameters to play with, and you can adjust those to yeah, get better approximations. If you have just one parameter, then you are going to get very coarse approximations like you have here in your first order filter. Okay.
Sir, if the function is rational, then can we say it is low pass? Or
Then what?
like the transfer function?
Transfer function is rational.
Yes.
Okay. So rational does not always indicate low pass. We will see an example soon.
The previous two examples, like RC and LC, you explained both of them were rational.
Yes. So now you can try this one, CR, and see what you think. Okay. So you can do that as a homework. So this is still rational, but it's not low pass. Just plot its magnitude response. You are going to get a high pass filter. Okay, so E and R. And the transfer function is of this kind. Still rational, but it is not a low pass filter. You get a high pass filter. to get ideal,
Sir, this is proper, right? Like the functions.
yeah, what?
It is not rational. It is proper function.
It is not rational. Why it is not rational?
Sorry, sir. It is rational, but also proper function. What I mean is, if the degree of denominator is higher than numerator, can we say it low pass?
Okay, so yeah, let's try to address that also. Let's look at this RL and let me call h of s and this I-O of s or I of s over V of s. So let us see what is this. R over SL plus 1 over SC, I think, right? Plus R. So this is SCR times some second degree polynomial. So this is strictly proper, right?
Yes, sir.
Filter or something else? Any SS
It
or
is rational.
yes? No, why not?
No, sir. It is rational and plus high pass.
And it is strictly proper, but I am asking whether it is low pass or it is not a low pass. So I'm just yeah, trying to have a discussion. So like you asked a question, right?
Band pass.
Right. So this we had already seen in our first year EE course. Yeah. So this is a resonant circuit. This is RLC resonance. Yeah. So I naught, if you remember, there is some resonant frequency at omega naught where peaks, and for other values, yeah, the response decays. Okay. So around this frequency omega naught, we have the maximum gain or whatever, and we have more and more attenuation as you move away from omega naught. So this is a band pass filter. Yeah. So we have an example of a band pass filter which we can relate to yeah, series resonance or parallel resonance, whatever. And here we have strictly proper transfer function which does not correspond to a low pass filter. Okay. So it's not always true that if you have strict proper function, then you have a low pass filter or something like that. You need to yeah, find the magnitude response and check how does it look like. Okay. So it may be low pass, it may be something else. But band pass and low pass are sort of yeah, closely related. Even high pass and low pass are closely related. So let me clear this. So I have low pass LPF, then HPF, and BPF, and there is band stop also. All of them are closely related. So these three we had seen. Band stop is yeah, just something where you have attenuation, so opposite of band pass. Yeah, it passes all other frequencies, but yeah, rejects some specific band of frequency. So this is band stop. Okay. So let us see how they are related to one another. Let's restrict ourselves to ideal low pass filter first. Okay. I mean all idealized forms. So none of these can be realized in practice. Ideal low pass, ideal high pass, ideal band pass, ideal band stop. Okay. But just in theory, let us see how they are related to each other. So frequency response of ideal low pass is something like this. Ideal high pass is maybe something like this. Band pass again quite similar to low pass but shifted at omega naught.
Sir, isn't the second one band stop filter?
Sorry.
The second one you have.
Okay. So yeah, band stop and high pass are also similar. This is omega is 0, and for band stop, yeah, you have something like this. Omega naught. Yeah, so high pass and band stop are sort of similar, but yeah, high pass attenuates all low frequencies, and after some cutoff it allows them to pass, and band stop attenuates yeah, specific band. After that it allows. So you can relate these two easily. You just have 1 minus this rect function, rect of omega. So this is rect omega, and if you take 1 minus of that, then you are going to get this, and this you can make it as big as you want as long as you have finite width, and yeah, you can make it as long as yeah, whatever the width you want to have here for your high pass. Using this trick, you can construct an ideal high pass filter. So in time domain, you get 1 minus, sorry, not 1 minus. So Fourier inverse of 1 is delta. So you're going to get delta in time domain. Delta t minus sync. So this is time domain response or impulse response of ideal high pass filter. This one. Just by taking inverse Fourier of this. Okay, so that's high pass filter, frequency and time. What about band pass filter? You can time shift this. No, sorry, frequency shift. Yeah, we want to have it centered at frequency omega naught. So do frequency shift of yeah, this frequency response. So in time domain, it will be e to the power j times whatever, yeah, e to the power j omega naught t times sync of t. This is going to be band pass filter. Okay, in time domain. And band stop again 1 minus band pass in frequency. So in time domain, yeah, delta t minus this. Okay, so you can get all of them from one another like that. So just go through this discussion. So this is what I'm writing here. Ideal high pass filter is 1 minus ideal low pass. So 1 minus the rect function, and then time domain is just yeah. And examples are all yeah, RLC components you can realize. Not ideal filters, but yeah, just low pass and high pass filters. Band pass, yeah, there is a frequency shift, and yeah, You can find the time domain expression for this and for band stop also. All pass is something which allows all frequencies to pass. Okay. So the magnitude response is constant for all frequencies, for all pass. All pass. Phase factor could be something, but yeah, the magnitude response is allows all components to pass. Phase could be constant, or it could be non-trivial function of omega in general. So this can be realized by just delta function. But there are other ways to realize this also. All pass rate, which we will see. Okay, so these realization examples you can see. Okay, just try out various circuit components and just try some permutations, combinations, and plot some frequency response, either using some software or by hand, whichever way you prefer, just to convince yourself. You can do these realizations using op-amps also. Okay, so if you are not aware about op-amps or not familiar with them, don't worry about it. But yeah, those who do, just I think all of you will know about op-amps. So yeah, not just with RLC, but yeah, with op-amps also you can realize these filters. So those are called active filters, and with RLC, whatever you get, those are called passive filters. Yeah, let me not get into those differences. Okay, so let's look at some applications now. Okay, so this will come up in circuit theory, and for EE and Instru guys, I think yeah, they will take courses on power electronics at some point, and yeah, let us see some relations in here. I think after that we can take a break. Okay, so any questions so far? Let me erase this. Maybe. Okay, so let's recall half wave rectifiers and full wave rectifiers. Okay, so I'm just going to draw them by a block diagram like this. Sorry. Say full wave rectifier. You can have half waves also. You can have half waves. These are not linear time invariant systems, but yeah, that does not trouble us in any way. We have a sinusoidal signal as its input. So this can be realized using diodes, 4 diodes and bridge rectifier you can have, and the output response something like this. Badly drawn, but yeah, you get what I mean. So same input in here, and you only get alternate lobes. So this is used to get DC waveforms from AC. In electrical engineering, you have this converters, AC to AC, DC to AC, DC to DC, and yeah, four combinations. Okay, I might have missed one or two, but yeah, AC to AC, DC to DC, DC to AC, and AC to DC. Okay. All four are required in some applications. Your application may require a DC source or an AC source, and depending on that, yeah, you have this converter. So these are AC to DC converters. So AC is yeah, both quadrants. You have your waveform, and DC is yeah, just one polarity. Okay. ideally you want a DC of constant magnitude, okay, something like this, which this is the idealization you are striving for, and this is far off that idealization. Yeah? Even though this is DC, there are fluctuations in here, which you can see here. Okay, so if you have just this bridge rectifier, you cannot maintain a constant magnitude like this. Yeah, so this is a bad approximation of this. So you need some processing on this to get a better approximation of this. Yeah. So whether this is LTI or not, yeah, we don't care right now. We got from here to here, we got our DC waveform, and now we want to approximate this if we can. Okay, so starting with this and using some LTI systems, can we approximate this better? So any ideas, anyone?
So we can use a capacitor.
So capacitor, right? It is an integrator, and yeah, sorry, you can associate its magnitude response with a low pass filter also. So yeah, 1 over S is what the Laplace transform of an integrator is, and this is 1 over j omega c using capacitor. So the magnitude response, yeah, it goes to infinity at 0, and then it tapers off. If you put an R, then yeah, we already saw what we get. So this is just with integrator or using just a capacitor. And this is our frequency response, and this is a low pass filter again. Not ideal or anything, but it is a low pass. Infinite gain at low frequencies and lower gain at higher frequencies. So why do we want to use a low pass filter? Is yeah, we want to get rid of this fluctuation. Yeah. So higher fluctuations corresponds to higher frequency components. Okay, if you have fluctuations in your waveform, that means yeah, there are relatively high frequency components if you do a Fourier expansion of your waveform. Okay, using sinusoid. So this is, both of these are periodic functions, and we can write a Fourier series for either of these. Okay, if they are not periodic, we can write a Fourier transform. Okay, but yeah, since we are dealing with periodic ones here, so let's stick to Fourier series. So there are high frequency components present, and we want to get rid of those high frequency components. Yeah, this is what we are striving for, ideal DC signal. So if we put a capacitor after this, or a low pass filter, either is fine. So just an integrator or a capacitor or LC filter, RC, whatever. RC will cause some power losses, so yeah, LC might be better, but anyway, that is for yeah, those who want to get into those details. But yeah, if you have something like this, okay, so this is ground. Immediately after this system, so low pass filter in cascade with a full wave or a half wave rectifier, what you get is something like this. So this is a half wave rectification. Okay, badly drawn, but and full wave is okay, I'm going to draw this badly. So these fluctuations are going to reduce. Okay, so using this capacitor, the waveform goes down a bit, but yeah, it does not go down to 0 up to some finite value. Then again it starts like that due to charging and discharging of capacitor. Capacitor does not discharge fully, and yeah, you have something like this. Okay. So these are one of the applications of filters, which yeah, double E and Instro guys, I don't know Instro guys whether they take power electronics or not, but double E guys and electronics guys will surely encounter such kind of circuits later on in their courses, and yeah, then you can relate this to these high pass filters and low pass filters which we had studied in this course. Okay, so this is for AC to DC. Then there are DC to DC converters also, and there also you do use low pass filters. Okay, so even for DC to DC, again there are some switchings involved which introduces some fluctuations, and you need low pass filters to filter out the fluctuations in your DC. Okay, so low pass filters are used even for DC to DC converters, and I think high pass filters are also used somewhere, maybe from DC to AC or something. Then band pass filters, yes, we had seen this in again first year EE course. So radio applications, if you want to tune your radios to some specific frequencies, so old analog radios, then of course yeah, you adjust your resonant frequency, which is the band pass frequency. Okay, so to pick out yeah, those specific stations. So there are these applications, and yeah, there are more also which I might have missed. So this is one exercise you can try. Yeah, so getting Fourier series of yeah, these rectified outputs, and then use the frequency response of the low pass filter. So whatever 1 over j omega c or whatnot, that times the Fourier series of this input waveform will give you the Fourier series of the output waveform. Okay, and you can then go to time domain by taking inverse Fourier series or whatever. If the expressions get too complicated, then okay, at least you should understand in principle what's going on. If you can do it by hand, well and good. Otherwise, yeah, at least the idea behind this exercise is yeah, to give you the application stuff of these things, and yeah, some mathematical analysis practice also, finding Fourier series of these waveforms. So I don't remember whether it is too difficult or not too difficult to find the Fourier series of these. May not be too difficult because this is just magnitude of this, for example, and this has delta function. Fourier series of this is just delta function. But yeah, magnitude and there is no property which gives direct Fourier transform of magnitude of x. So yeah, this may not be straightforward. But anyway, try it out if you can. Otherwise, at least in principle, you should understand why this exercise is there. So there are discrete filters also, which are analogous to this and which can be realized using delays instead of integrators. Okay, so adders and multipliers are anyway there, but in place of integrators, we just use delays. Okay, and we can have finite impulse response or infinite impulse response. So FIR or IIR filters. And how to design that? Yes, I will give you at least the philosophy of designing discrete filters. So there is a straightforward recipe, not straightforward, but yeah, a well-studied recipe of designing continuous time filters. So continuous time filter. I mean, it's a mechanical procedure with some steps. So given, so yeah, this is sorry. Okay, so pass band is okay, band of frequencies which you allow to pass. Then stop band frequencies is the frequencies which you want to stop, and then there are ripples. Ripples corresponds to fluctuations, etc. in both pass band and stop band. And depending on these parameters, you can design continuous time filters like Chebyshev or Butterworth, whatever. There are mechanical procedures to construct these filters, which I will not get into. But there may be more. So usually these things are not studied in the first course, and these are not too difficult, but it requires a lot of bookkeeping. Okay, these are mechanical procedures, but yeah, requires a lot of bookkeeping, and yeah, you need to work out maybe one or two examples to get a feel of this. So these are the filters. Okay, filter design. I'm just giving two examples. There could be more. So this is in continuous time. Yeah, and depending on your requirements, so design specifications, you then design your filter. Okay, whichever one suits your specifications in continuous time. Okay, and if you want to design discrete filters, then yeah, there is something called as bilinear transformation. Okay, to go from continuous time parameters to discrete time and vice versa, from discrete to continuous. Okay, so using this bilinear transformation, you convert your discrete specs into continuous specs, design your filter using continuous specs, and then, excuse me, once the design is complete, you go back from continuous to discrete. Okay, using this bilinear transformation. So once you understand continuous time filter design, that's all you need to design either continuous or discrete. With this bilinear transform, you can always do your design in continuous time and then go back to discrete domain to get back to discrete filter. Okay. As far as realizing those discrete filters in hardware is concerned, you always have your delays, multipliers, etc. Okay. So that realization can always be done. Continuous time, anyway, no problem. You have active, passive integrators, etc. You can realize them. Okay. So that's basically the idea behind discrete filter design. Yeah. All right, so that is all I have as far as that goes. So these examples we will see next week possibly. Both these examples of filter design. Where was I? Yeah. Okay. So there are two examples here which we will see, and there are two examples of sampling also. Okay, so we can take a break now, maybe 6 minutes, and after that, yeah, we can start with sampling. If you have any questions, then we can take some questions also after the break.
Yes, sir. Sir, I have a doubt.
Okay, so maybe after the break, is it okay?
Yes, sir.
Take a break and then, yeah. Please remember to ask this out after the break. Okay, so maybe I can take the doubt now. Someone had a question?
Yes, sir.
Yeah, please go ahead.
Like which should we use? Means, out of those filters, which can be more useful?
More useful. That
Yes,
depends
sir.
on, right?
Like you have experienced some types of low pass filters. So, what should be our purpose if we use these filters? Which one should be the better one? Because how should I differentiate from one filter to another means in using in a circuit?
There is a lot. Heard a lot of noise. Okay, you are again on mute. So yeah, I heard your question, but I missed some bits. Okay, so you said that how to choose a specific filter, something like that.
Yes, sir. Yes, sir.
All right, you are again on mute. Can
Uh, Sir, am I audible? I think, sir, I'm typing in the text box. Uh, Hello, sir. Can you please see the chat box? I texted it there.
Hello, sorry everyone. My screen got froze and yeah, I had to reboot my system. Yeah, I'm just sorry for that. I hope everyone can hear me. Am I audible?
Yes, sir.
So just give me a moment. Okay, I can see the question. Yeah. On what basis we should choose a filter? Okay.
Sir, please share your screen.
I hope it is recorded. Yeah, recording is started. Yeah, so basis for selection is okay. So basis for selection is your application, whether you want a low pass filter or a high pass filter or a band pass, band stop, whatever. So that is one criteria for choosing your filter. The other is then how much ripple or distortion you are allowed to have in your application. So, uh, like how better you want to approximate your ideal filter. Yeah, of course, to arbitrary accuracy you cannot approximate, but yes, there are better and better approximations if you are ready to put in more cost. So, by more cost, I mean increasing the order of the filter. Okay, so if you are willing to have more degrees of freedom, then in some sense, yes, you are going to get better approximations. So that is another criteria behind yeah, which uh, which sort of realization you want to choose, the order of the filter. So application and then design requirements. Okay, how much distortion uh, you are allowed to have. So those are the two things, yeah, based on which you can select which filter you want to have, and of course continuous or discrete. Of course, continuous in practice, yes, you will work with digital signals, etc. So always discrete, but maybe in some old analog circuits or whatever analog applications, you may want to have continuous time filters. So yes, there are analog applications of continuous time filters, and of course, yeah, discrete or digital filters, yeah, in all digital or discrete applications. So apart from that, is there anything specific in the question? Okay, okay. So yes, that's what I can say. But yes, if you can make your question, if you want to make it more specific, then yes, we can have discussions based on that also. Okay. So this is just a general idea behind yeah, which type of filter you want to choose. But yes, as you go more into specific applications, then of course that application or your design requirements will drive what filter you want to choose. Okay, any other questions?
Sir, if we are given some transfer function, then only by verification, I mean, by finding the magnitude and all others, we can find whether it is low pass or high pass. We cannot say it from the function itself, right?
Okay, so let's come to sampling now. We had
Sir?
yes, please go ahead.
Yes, sir. Sir, I was asking like, if we are given a transfer function, then we cannot say whether it is low pass or high pass unless we check its properties.
Yes, yes, for yes.
So if we don't know how to find properties, I mean how to find those properties. Like if we are given some RLC circuits, then we can do. But if we are given some other, then
So what other thing you have in mind? Like, I mean, realizations I can think of are using RLC or like op amps or something like that. And in discrete time, just delays, adders, etc. But how to realize filters apart from these things? Even you can have mechanical analog, spring mass, damper, whatever. With that also, you can have low pass and high pass design. Uh, but apart from that, yes, I cannot think of any other realization. Uh, so if you have anything in mind, then yeah, please share with me. I mean, with all of us.
no sir, I just wanted to know how other realization. It is fine.
I don't know if there are any other realizations possible or not. I'm not saying it is not possible or whatever. Yeah, so you can give it a thought if there are other ways to realize that. And yes, how it is related to RL and C in is I hope it is clear.
Yes.
So one pattern, yes, which we can see here is maybe 1 over S plus A. All transfer functions of those kind are low pass filters, yeah, at least in the first order realization. Yeah, that just follows from the magnitude response of 1 over S plus A. I think we drew it sometime back. Yeah, so it looks yeah, something like this. Yeah. So 1 over S plus A, that first order realization is always a low pass design. And S over S plus A is always going to be a high pass design for first order. I don't know whether that generalizes for higher order or not. You can check. Yeah. I don't remember doing this, but yes, and I also don't remember seeing it anywhere. So just take it whether for second order also it holds. Band pass filters cannot be realized just with first order circuits. Okay, so just with R and C or R and L, you cannot realize band pass filters. Yeah, you'd need second order filters, okay, to realize band pass filters. And we saw that, yeah, with series RLC, so this is high pass, first order. Yeah, series RLC, you can have band band pass filter. So that has a numerator polynomial of degree 1 and denominator polynomial degree 2. So you can see it, but you can identify some pattern here. Uh, Whether that holds in generality or not, yes, I wouldn't say so, but who knows? Yeah, and if you take maybe voltage across L or C, you will get some different transfer function, and then yeah, from the magnitude response, you can see whether it is low pass, high pass, or whatever. Yeah. And then from yeah these observations, at least you will be able to identify some patterns, and based on that, then yeah, you can decide like whichever then how you would want to realize higher order filters. Okay, so putting more components, etc. How it's going to affect your realization. Okay, which parameters you want to choose? Not parameters. I mean, which quantities. So, yeah, voltage across the inductor or capacitor, or voltage across R is what you want to choose, or whether you want to choose a current or something else, and what sort of fractions or transfer functions are going to give you the required realizations. Yes, with some by trying out some examples, you may see some patterns, and based on that, for higher orders, yes, you may have some ideas. Okay, but in general, yes, I have not seen any theorem or yeah, something like that which says that okay, this is what it is for higher order filters or whatever, second order, first order, etc. But we had already seen some patterns for first order. At least that should be clear. First order filters, using them you cannot realize band stop or band pass. Yeah, just high pass and low pass you can realize. For band pass and band stop you need at least order 2. Okay, so yeah, let's stop with that. I think we have had a long discussion on that. I want to start the sampling now. Okay, sampling, yes, we had already seen. You have a train of impulses and that's how you go from continuous to discrete. We have continuous waveform and we are multiplying. Train of impulses. That's going to give us the sample signals, which is our discrete signal. And in the frequency domain, yes, we have a convolution. So frequency spectrum of this, like this. This shape can be yeah, deceiving. Okay, so don't get deceived by this triangle or frequency response of finite width. It may not always be like this. Here also we have train of impulses. So if you have compressed train of impulses here, they will be sparse out in the frequency domain and vice versa. If you have sparse out train of impulses here, then it will be compressed in the frequency domain. Yeah, this we have seen before, how these two are related and how the spacing is related also. So if your frequency spectrum, okay, so this is Fourier transform of this continuous time signal. And if this is of finite width, okay, so what do I mean by that is yeah, the frequency or the Fourier transform is 0 after some cutoff frequency. Okay, so these sort of signals are called band limited signals. Okay, why band limited? Because the frequency spectrum is finite. I mean, it is non-zero only over this band of frequencies. After this band of frequency, the frequency spectrum is identically 0. Okay, so those kind of signals are called what did I say? Band limited signals. Yeah. So this is band limited. So band limited imposes a constraint in the time domain. Anyone, what is that constraint in the time domain? So it is band limited
It
in the
should be periodic.
periodic. Why periodic? Does periodicity have anything to do with?
Okay, no.
Yeah. This is uncertainty principle, right?
It will be infinite.
Right. The impulse response cannot be time limited, okay, in some sense. So impulse response cannot have finite time width. It has to have infinite time width due to uncertainty principle. Yeah. If you try to localize in one domain, yes, you get complete delocalization in the other domain. Yeah. So band limited signals, yeah, are not time limited. So time unlimited, maybe. I don't know whether this is formally used or not, but yeah, for our understanding, yeah, time unlimited is band limited. Band L, let me write. time limited. Band unlimited. This is from uncertainty principle. Frequency time localizing. Band B unlimited. So this is from uncertainty.
So like the converse is also true. Like if it is time unlimited, then it has to be band limited.
Yes. Provided its Fourier transform exists. No, sorry. Oh, yeah, you are right. This is not true. Okay, so only this is, yeah, thanks. So band limited in one domain surely implies it is unlimited in the other. And yeah, this is, okay, so yeah, that's a good observation because Gaussian is, yeah, neither time limited nor band limited. Okay, so yeah, the example of this is Gaussian, which is spread out in both domains, so both time unlimited and band unlimited. So thanks. But if you have band limited, then surely you lose that property in the other domain. So this is just one way implication. Yeah. I hope this is fine. Band limited surely implies time unlimited. Converse is not true. And yeah, time limited surely implies. Wait. Yeah, time limited surely implies band unlimited because otherwise you will violate uncertainty.
Yes, sir, got it.
So this can be deceptive. Yeah, this is only true for band limited signal. These kind of shapes of frequency response having just finite bandwidth. It's not a bandwidth actually, but yeah, you get what this means. Okay, so we had also seen few weeks back this relation between multiplication and convolution property and how the spectra of the continuous time and discrete time signal are related. Yeah, so let's start with band limited signal. Okay, so we have unlimited time unlimited signals which are band limited in the frequency domain, which we are trying to sample. So we get discrete samples from this, and in the frequency domain we are going to have convolution of this with this shifted impulses, which is going to be periodic extension of this, right? So as a result of this, here is sampled time signal, whatever, and its Fourier transform is going to be periodic due to convolution with the impulse. So something like this. So provided this happens, we can we reconstruct the continuous time signal from the discrete sample? Should be straightforward, right? In principle, I'm saying, yeah, not in practice, but yeah, in theory. So anyone, this should be easy enough. We started with this continuous time signal which had this Fourier transform. Then we sampled it. So as a result, we got this. So this is time domain and this frequency. Can we recover the continuous signal from this? We want to recover this from the periodic extension.
So can we multiply by rect?
Yeah. So ideal low pass filter. Yeah. So forget about the fact that it is not realizable, but yes, in theory, yes, you can have rect function and just keep this with an appropriate gain factor. There might be some scaling, does not matter, and just get rid of this. Okay, so if you do that, then okay, so this is LPS here, and as a result, we recovered our original spectrum. So multiplication by a low pass filter in time domain, that is convolution by sink in the frequency domain. So going from here to here, you do convolution with sink, right? SI. So all these impulses, you convolve that with a sink function. So yeah, corresponding to each impulse, you will get a shifted sink, and yeah, you take sum over all impulses, and that's going to give you back your continuous time signal. Okay. So in theory, you can always reconstruct from your sample signals, your original signal, provided it was band limited to start with, and these shifted spectra of your original signal, they don't interfere with one another. Okay. So how to guarantee that they won't interfere is, yes, your train of impulses in frequency domain is more spread out, right? If they are very closely packed together in frequency domain, then yes, you are going to get interference. They are not going to be, yeah, like this. They are going to interfere with one another, and in that case, you won't be able to reconstruct your exact continuous time signal, even in theory. Forget about what you can do in practice, but you cannot do it in theory also if they interfere with one another. So you want to have more spacing in frequency domain, which means you have compressed impulses in time domain, which is sort of intuitive, right? If you sample it with a high frequency, or I mean, yeah, with samples which are close enough in time domain, so something like this, then yes, you can see why it makes sense. Yeah, the closer approximation you have, the better chances you have of reconstructing the original signal from its sampled signal. Okay. And if you have sparse sampling, so you have spread out samples in time domain, then okay, you are keeping this and maybe this, something like that, then of course in between, yeah, anything can happen in general. Yeah. So yeah, that was very loose, but hope you get that this argument is at least in some sense intuitive. Why do we want to have closed, I mean closely spaced train of impulses in time domain to have better chances of recovery from discrete samples? Okay, so that is for band limited signals, by the way. Yeah, so given band limited signals, if you sample it, yeah, nicely, quote unquote nice, then you can reconstruct in theory, yeah, using low pass filter, ideal low pass filter. So what about time limited then? Okay, if your frequency spectra is not band limited, maybe something like this. So time domain signal could be time limited or time unlimited. We know for sure that its Fourier transform is not band limited. And now if we sample it, can we recover it? So not band limited. Sorry, this is badly drawn. So this is in frequency domain, not in time domain. So we are sampling in time. In frequency, we are going to have a convolution. So let me explain this again. We have some time domain signal whose Fourier transform is not band limited. Yeah, it does not become zero after some finite frequency interval. It continues. So for such signals, can we recover the continuous time signal from its uh, sampled signal? Is the question clear?
Yes, sir.
Yeah. So I have a signal which is whose frequency spectra is not band limited, and I have sampled that signal. So I'm doing sampling in time domain. Sampling in time sampling. This is what happens in the frequency. So there is a convolution here. So like we saw here, we can reconstruct the time domain signal exactly in theory. Can we do the same for this case? Signals which are not band limited. So any suggestions?
So we'll never get back the exact
Sorry,
signal back.
say it again.
Sir, we'll never get back the exact signal.
Yes, exactly. Because you are going to have interference. Yeah. So this gets convolved with maybe this impulse at zero. It stays as it is. But once you convolve it with yeah, this shifted impulses, there is going to be this interference, no matter how widely spaced they are. Yeah. At some point, there is going to be this interference because this property being not band limited. So you cannot avoid distortion in frequency domain, no matter what you do. Yeah. How close you sample in time domain, whatever, it's always going to be this distortion. And exact recovery is never possible for signals which are not band limited. Yeah. So that is the idea behind the Nyquist sampling theorem. Okay, this exact recovery is possible only when the signal is band limited. Yeah, so Nyquist criteria for recovery is valid only for band limited signals, and it is not true for band unlimited signals. So don't get deceived by this triangle or some other shape. Yeah. So this is only depiction of signals which are band limited, and Nyquist theorem says that okay, if you sample them with high enough rate in time domain, then exact recovery is always possible using low pass filter in principle for band limited signals. So the next question is how high the sampling rate should be, okay, to have exact recovery, and that is also sort of intuitive from this again convolution multiplication property. Yeah. So if you go back to this train of impulses, so if you sample them with frequency omega, then you start with 0 and you have omega naught here minus omega naught here and in time domain. So this is periodic with t is equal to 2 pi over omega. So this is a periodic signal, that's why we have this period t. So higher the omega naught, the lower is t. Yeah? So they are closely spaced in time domain if they are spread out in the frequency domain. So in other words, if you have high sampling frequency, yeah, you have very densely packed train of impulses in time domain. Okay, so how large the rate of sampling should be? Okay, so you want to avoid any sort of interference. Yeah, so if this width, for example, yeah, this is 2 omega, let's say, 2 omega c maybe I will write, or omega m. Okay. So this is plus omega m, and this is minus omega m. Yeah, that is the band limit of my continuous time signal. So its total bandwidth is, let's say, 2 times omega m, and I want to sample my continuous time signal such that I avoid any interference of these shifted waveforms. Okay, and where these are centered, these shifted waveforms, they are centered at sampling frequency, omega naught, minus omega naught, etc. Because if you go back here, our discrete impulses are at omega naught and its integer multiple. And now, what are these frequencies? This one and this one, for example. So this is plus omega m, this is minus omega m, and then this is this waveform shifted by omega naught. Okay, so this point comes to this point, shifted by omega naught. So this was minus omega m. So this point will be omega naught plus omega m. Omega naught, sorry, minus omega m. And this will be omega naught plus omega m, and so on. Okay. And you want omega naught minus omega m to be strictly bigger than omega. If you ensure that, then you are not going to have interference. So this omega m will be strictly bigger than omega m is this point, and omega naught minus omega m is this point. Okay. So to ensure that no interference occurs, we have to ensure this quantity, and that's where sampling theorem comes from. If your sampling frequency is strictly bigger than 2 times frequency of your signal, you can always have exact recovery. Okay. So I think I'm out of time. So let me stop here. I will take questions if there are any. Otherwise, we'll continue this next Wednesday. So thank you all for attending, and see you next week.